When I'm working in Euler's method problem, I like to use a much more expanded version of the table that's being presented in my lab math. If you look in our textbook, this more expanded table is used, and I believe there's also an example where they go through and talk about each of the pieces. I want to explain to you really quick how I do this and what each of these pieces are in my table. So I like to keep track of how many iterations or how many times I've done this. Sometimes you will be asked to find a specific value. It's also possible that you'll just be asked to perform a certain number of iterations. So at the end of this first row, I will have completed one iteration of Euler's method. X sub n and y sub n are the starting x and y values for that row. And if you think of this in function notation, we're used to seeing f of x. So it's at the x value that's inside the parenthesis. And f of x is just a fancy function special way of saying the y value. So what this is equal to is the y value. So what we're being told here, when we're being told that y of 5 is equal to 2, is that when the x value is 5, the y value is 2. The next piece of information I like to store in my table is the derivative or the slope value on that graph at that point. If you have watched the lecture video posted on our Moodle page, Khan Academy gives a really great graphical example of what is happening with Euler's formula, where you're following these tangent lines for very small increments. And the increments are the step size, which we've been asked in this problem to use as 2/10. We only want to follow that tangent slope a tiny, tiny distance because we know tangent slopes are only good at one particular point or in a very, very close neighborhood around that point. If our step size is too big, our approximation is going to be way off. And really, in general, the smaller and smaller the step size, the better your approximation is going to be. So what we have here with this differential equation, y prime is the same thing as dy dx. dy dx is just another format for derivative. And in Calculus 1, the very first application, we typically learn for derivative is slope of the tangent line. So we want to know what slope should we be following. And this differential equation tells us an exact formula using x and y that we can use to figure out what the tangent slope is. It says take 2 divided by your x value, which is currently 5, and multiply that by the y value squared plus y. So inside the parentheses, we end up with 4 plus 2, which is 6. So we have 2/5 of 6, which is 12/5. Now you can keep that as a fraction. We want to eliminate as much error as possible, and one way that we introduce error into these problems is with rounding. 12/5 as a decimal is an exact number, so it's not really an issue for us to change 12/5 into, I think, 2.4. Remember back to algebra class, when you have a slope, you can always think of it as a rise over a run. So if we were to move 1 unit in the x direction, in order to follow the tangent slope, we would have to move 2.4 units in the y direction. But we don't want to move 1 unit in the x direction. We only want to move 0.2 units in the x direction. So the way that we can introduce an x step of 0.2 is to multiply top and bottom by 0.2. And that's exactly where this part comes from. We want to use our current y value and move along the tangent slope, but only a very small step. So the way that we introduced a small step of the tangent slope is by multiplying them together. That tells us how much we should move in the y direction to get our new y value. X sub n plus 1, that's our next x value. If we're doing a step size of 0.2, we're going to use the old value of 5 and add 0.2, and our next value would be 5.2. The next y value is going to be the current y value of 2, plus we're going to follow the slope value of 2.4, but only for a step size of 2/10. So we need to calculate 2.4 times 2/10, which is 0.48, and that we need to move 0.48 away from 2, and it's a positive 0.48, so we get 2.48 as our new y value. I wouldn't typically write work within the table. I would write it off to the side, or I would write it below, but I want you to see, at least in this first row, where all these numbers are coming from. So now on the second iteration of Euler's method, my new x value is 5.2. My new y value is 2.48, and that's the x and the y value I want to use now to continue on filling in my table. So that's the x and y I'm going to use to calculate dy dx. This derivative formula up here is how we calculate dy dx. So we've got to do 2 divided by 5.2 multiplied by 2.48 squared plus 2.48. And we're definitely going to want to change this to a decimal. So when I pop this into the calculator, I get a tangent slope of 3.319. I'm using 3 decimal places here because in this problem they are expecting my answer to be accurate to 2 decimal places. The new x value is just going to use the step, so that's going to go up to 5.4. But for the new y value, we need to take that old y value of 2.48, and we need to follow that slope, but only for the distance of our step size. So they get multiplied together. And I get a new y value here of 3.144. And we want to continue this on until we get to a value of 5.8. So on the next line, our third iteration is going to start with 5.4 and 3.144. We need to use that x and y values to figure out the slope by plugging back into the differential equation. The new x value is just going to increase by the step size. And then we can get the new y value by taking our old y value and adding the step size times the derivative. So you just need to calculate the derivative and plug it in here, and then transfer down those new values. And at the end of the fourth iteration, we will have an x value of 5.8, and we will have the y value that goes with it.